Dear participants, welcome back to ThalesNano's new webinar about the high pressure CO2 hydrogenation towards variable fuels using the Phoenix flow reactor in the gas phase. So today our guest speaker is Andras Shapi, the Assistant Professor of Department of Applied and Environmental Chemistry at the University of Szeged, Hungary. So as usual, after the presentation, you will have the opportunity to ask, and your question will be answered by Ali Shan Malik, a postdoctoral expert of CO2 hydrogenation, also from the same department at the University of Szeged. So please feel free to ask all your questions during the webinar, and we are happy to answer all questions raised. So I let the word now to my colleague. Thank you and enjoy.
Hello, welcome everyone. Good afternoon. This is Andras Shapi speaking from Department of Applied and Environmental Chemistry, Szeged University, Hungary, and it's an honor that I can give you a small talk and introduction about high pressure CO2 hydrogenation, how we do it in our lab in this ThalesNano free webinar this afternoon. So first of all, I just wanna show, maybe if you come to Szeged, please let us know. We are happy to have you. This is our famous church over here, the so-called Dome Square. And then here are the chemistry buildings, organic chemistry, inorganic chemistry you can find here. And behind this building, you can find this one. And this is where we are located and all our lab located here. So the finished reactor is somewhere here, I think, in this window where we do the CO2 hydrogenation at high pressure in this reactor. And of course, if you come to Szeged, you should try our really famous fish stew and soup if you come. And so here you can find a group. You can see this is Professor Zoltán Konya, the head of the department, also vice rector of the university. And then these are all the people who are in somehow participating in this work, and then take it in to part. So we're going to talk about CO2, and then we can say exactly CO2 is a problem. Here is the concentration in ppm of CO2 in air, and you can see how it's drastically increasing. And then I just read an article from 20 days ago, so it's pretty fresh, and then the concentration reached 420 ppm in air, which is pretty high. And then this is what Peter Tan, the senior scientist in Hawaii, said this, that we are adding roughly 40 billion metric tons of CO2 pollution to the atmosphere per year. That is a mountain of carbon that we dig up out of the earth, burn and release it into the atmosphere as CO2. So anyway, he says that one of the highest priority must be to reduce CO2 pollution to zero at the earliest possible date. And I think on one side, I'm agree with this Peter, and yes, we have to do something with the CO2. And CO2 can be used in a lot of way, which is a good news. But of course, you cannot produce dry ice, all of the CO2, because we don't need them. So the future of CO2 is to use them as a fuel. And here we can see a couple of examples where we, researches are going. So one thing based on biology, the algae can produce really nice fuels. I mean, you can produce algae, which is then after burning, you can also produce energy out of it. And these algae are produced from CO2 by photosynthesis, like, this is how biomass work. And the other one is that enhanced fuel recovery, they push back CO2, and then that helps fuel to come up. And this is also a way to use CO2. And we are chemists, so this is our way. And then this is one of the future to use CO2 as a chemical and then convert it into useful fuels. And one of the main reactions, how can you do that, is to somehow you have to reduce CO2. You cannot oxidize it anymore, so you have to reduce it. So with hydrogen, that's the easiest way. Also in a bracket, that's a question that how will you produce hydrogen, but CO2 hydrogenation is the main reaction where you can produce CO, methane, methanol, DME, or of course connect the carbon atoms in next to each other and then produce, C2, 3, and so on, C5 fuels, which is, the future plan. And so this is used in industry. So you can see here, this is the Georgia plant in Iceland, which is able to produce 4,000 tons per methanol per year. And these are the conditions. And then, so this is a CO2 hydrogenation reactor to produce methanol. But you have to see that, so this is a market data for example, the small chemicals for methanol demand, and then this is for the dimethyl ether demand. So you see that this is a forecast that the need for methanol will be really, really high, and also the same for DME. However, that means that it's a good idea to produce methanol or DME from CO2, but you have to see that this big demand is resulting in the really, really decreasement or decreasing price of methanol. For example, this is what you can see here in the last couple of months. This is how per ton, per euro of methanol is just decreased. So maybe producing methanol or DME from CO2 hydrogenation won't be the best, because activating CO2 is not that easy than, produce methanol from the regular syngas procedure. And so maybe in the future, we have to find a way to produce higher hydrocarbons, C2 plus, or especially maybe C5 plus hydrocarbons, and produce them from C5. This is how can we concentrate more carbon atoms and then produce fuels from CO2. So this is kind of the background why we try to do this. And then our idea is that, okay, try to do methanol, but the main idea is that we have to produce C5 or higher fuels from CO2, which is not an easy task, but a lot of research is going that way in the last couple of years. And then also we have a background of nanotechnology, and then designed catalysis with high surface area, and also a background of atomic level understanding of reactions. So know the reaction mechanism, and then that's how we're designing a new catalyst for new reactions. And then so all those industrial significance and needs, and then our research background showed us, and then go to the way that we have to, this is how we were motivated to produce, higher fuels from CO2 hydrogenation. So I know this is really, you don't have to uh, look into deep in. So this is the mechanism how CO2 hydrogenation can be done. This is surface mechanism on different catalytic surfaces in heterogeneous catalysis. The main stuff why I want to show is this, that from CO2 there are different pathway, but mainly you can produce CO or methane or methanol. This is the three-way. Anything what you want to do, firstly, this is going to be the first way where you can push your CO2 towards. So this is the basic mechanism. And then, so if you want to go higher, not just produce methanol or DME, or we want to produce C2, C3, and so on, we have to use a so-called tandem catalyst. We have to do two reactions at the same time. One reaction will be to produce, for example, CO or produce methanol. Okay, this can be, and then from those side products or intermediates, we can produce higher fuels. So one thing is to through the CO mediated route is the so-called like the Fischer-Tropsch synthetic route what you can use, and the other one is the methanol mediated transformation. And then reading a lot of articles and mechanism and kinetic studies, it says the metal mediated transformation due to the mechanistic background will be more favorable. So our idea is to do metal mediated transformation. And so this is how it can produce. So you produce a nice tandem catalyst which is able to produce methanol from CO2 and then also produce hydrocarbons from methanol. So this is our mission statement, to produce this kind of catalyst. And then for this approach, we will need high pressure. Without high pressure, it's really hard to solve at ambient pressures. We tried it, but high pressure reaction is the key. We have to push together these carbon atoms. So that's why we started to use the Phoenix reactor. And then if you go to the homepage of ThalesNano and check the Phoenix, you will find this picture. And then as you see, this reactor is mostly for liquid and gas phase and liquid phase high pressure reactions. But we a bit transformed it and then used them in high pressure gas synthesis with a success. So the reactor is here. So there is a two-way heating uh, over here. So there is a tube reactor over here from a stainless steel part, and then gas can come in from the bottom and go out through the top. And there is a back pressure regulator. With that you can adjust the pressure up to 100 or 200 bars. And then we use the so-called gas module, which is able to communicate with the back pressure modulator. And then with this, you can adjust different flow rates. With this guy, I think you can go up to 100 mil per minute. So on one reactor, we have one of these gas module, and we feed the reactor with a CO2 hydrogen mixture from a cylinder from 1:2 or 1:3, 1:4 ratio of CO2 hydrogen mixture. And then another reactor, we have two gas module where we can mix the CO2 and hydrogen as we wanted to do that. So when the gas is coming through the back pressure modulator, so it's going to atmospheric pressure, and then this gas is preheated and then going to our GC, and the GC is calibrated for all kind of products what we can see. Of course, the CO2 as a not a product but a reactant, but for products for CO, methane, methanol, C2 plus, C3, and so on. So this is how we put together our system, and this is where you can see it all together. So here we put about 100 to 200 milligrams of catalyst with a regular flow rate of 30 to 50 mil per minute. So the gas is coming through here, go through the reactor, through the back pressure modulator, and then it's going to the GC, and then we collect the data, and then we can follow the products what we formed. So let's see what we got. Before I go to the high pressure results, I just want to quickly show you a couple of atmospheric pressure results just to see. You can see that how we were motivated by designing our catalysts earlier. So, in industrial catalyst, usually the problem is that, of course, you use nanoparticles because they have higher surface area, and then the number of kinks and active sites can be different compared to the bulk phase. But sometimes you can lose the size effect as you just see this is industrial catalyst, and you can see nanoparticles from 1 to 2 nanometers up to 20 nanometers. So the size distribution of the nanoparticles are pretty broad, and then this is what we try to avoid, and then we're designing a catalyst. And what we use for this is nanotechnology, and then we're designing interfaces. I think this is a really nice example. So this is a sandwich with CO2, platinum ceria, and then what they do over here, I'm sorry, I forget to put the reference here, but this is in Nature Communication paper of Yamada et al. And Professor Samoy. And so if you have a sandwich of platinum ceria silica, the reaction of formulation is not going. However, if you have a ceria platinum silica, the reaction is going, which showing the direct evidence of how interface is important, and also, of course, nanoparticles and size is really important. And the other tool what we have is the molecular level understanding of the reaction. So we know what's going on with the molecules on the surface, on the reaction condition, what's going on with the catalyst. And with this knowledge, we can, that's how we can go further with designing our new catalyst in the way. So just quickly, we can produce, these nanoparticles with a narrow size distribution. These are platinum nanoparticles. So this is not, separately 2, 5, 7, whatever size nanoparticles we can produce from copper, from cobalt, platinum, cobalt alloys, and so on. I just want to show. And also, for designing interfaces, we're using the so-called mesoporous oxides. So these oxides you can see here with the hard template method, you can produce them has a high surface area. So if you buy a cobalt oxide in the shop, the surface area, BT surface area will be about 5 to 50 square meter per gram. However, for these materials, you can reach up to 200 of this. And so then we can, with design combining, we put together these oxides with our nanoparticles. And then just a couple of quick results. This is one of my favorite, however, it's a bit old, but I really like this. So this is commercial platinum cobalt catalyst. Okay. This is a platinum on silica surface, so inert catalyst. And this is platinum nanoparticles with control size on our designed cobalt oxide surface. We run CO2 hydrogenation at atmospheric pressure. And here you can see, I'm sorry it's in Hungarian, but I will translate to you quick. So this is temperature over here, and this is methane formation on the y-axis. So the blue one is the platinum SBA15, so the reference state, which shows that there is no methane. Yeah, usually platinum is producing CO, but on SBA15 as an inert support, you won't see too much conversion. However, the black one shows the commercial catalyst. You see that, okay, some methane just started to form higher than 600 Kelvin, and then it started to decrease. However, our design catalyst, you can see it's showing really high methane formation, even at lower temperature, and it's very stable. So anyway, I just want to show that designing looks really nice, and also not just conversion, but also the selectivity wise, we can change selectivity. So this is our design catalyst producing 100% of methane at ambient pressure, and not just the designing, but also these molecular level understanding can help us a lot. So here we find that the cobalt manganese oxide structure shows a really high methane selectivity, even to a high temperature. However, thermodynamically, it's not a favorable reaction, but our catalyst still showed a lot of methane, and then we didn't know why this was happening. So we tested our catalyst with EDX studies, and then we could see that how the manganese cobalt oxide spinel structure after the pre-treatment moved to a mixed oxide structure, and then after CO2 hydrogenation, it moved to a cobalt manganese oxide structure. We could follow this for the catalyst, and here we can see in the hot EDX spectra how. So this is a picture of the green dots are manganese, the red one is cobalt, and then this is how, after pre-treatment, how the atoms moved, and then finally how interfacial cobalt islands formed on the surface of manganese oxide. So this is how we think about them. And then the ambient pressure XPS on the reaction condition, we could see that how cobalt 2 is moved to metallic cobalt. However, manganese 2 plus remain the same. So we have an interface of metallic cobalt manganese O at the surface. And then with the IR spectroscopy, we could see how the mechanism went through. So the main stuff is that we could say that we had a high activity and high methane selective, even at a high temperature, which was attributed to the special cobalt manganese oxide interface which produce the formate route which help us towards the methane formation. So this is the ambient pressure backgrounds, and these are our further results, based on CO2 hydrogenation what we have. And then now I'm just coming back from this stuff to the results of the high pressure reactor. So this was the background, and this is one kind of motivation where we should go. So also, we designed a catalyst where we produced platinum, rhodium, and ruthenium nanoparticles sub 2 nanometer size. So the platinum was 1.4, rhodium 1.1, and 1 nanometer ruthenium nanoparticles with a narrow size distribution. And then we produced an MCF17 silica support and also a mesoporous ceria support. MCF17 was kind of, we wanted to use as a reference state. And then so we just add all the nanoparticles on the surface and test it in the high pressure CO2 hydrogenation in the Phoenix reactor. So in the case of platinum, you see a decent conversion of 20%, but with a really high CO conversion, CO selectivity, but up to a 10 to 15% of methanol selectivity, some DME at lower temperatures. When we put the platinum on ceria, it was pretty similar. It was interesting. Maybe we had a bit more methanol selectivity, but otherwise, CO was the main product here. When we moved to rhodium, the conversion of CO2 went up from 8 to 5% to 20%, but the main product was mostly CO. If we use the MCF17 support with some methanol there, and then it was interesting when we put it the rhodium on ceria, we have a nice interfacial effect, and then we could see much more methane, which wasn't visible in the case of MCF17 supported rhodium, and the conversion was way higher. And then we find the highest conversion with ruthenium samples, but the main product was mostly methane. Here you can see, and even though when we put the ruthenium on ceria, the conversion was a bit higher, but the product was mainly methane, which is, it's not C5, but it's still, a nice product. So we try to start to produce mixed bed catalyst and tandem catalyst from these, and then we mixed this ruthenium MCF17 catalyst in a mixed bed with ZSM5, but there was not a big success over here. Maybe we saw a bit more methanol, but not a big decent one. And then we used the dual bed. So firstly, we added the 1% of ruthenium sample and then the ZSM5. Then we see a bit more CO, but otherwise, the main product was methane in this reaction. This is the catalyst performance comparison over these reactions. So we're still working on those, but beside, we started to check, and this is a special catalyst where we use sub-2 platinum nanoparticles, and then we put it on the surface of a hierarchically porous polymer. So we have a nice collaboration with Korea, with Professor Myung Seo, and so they can produce these special HPP polymers where they can tune the number and also the sizes of the mesopores and the numbers of the micropores. So the micro and mesoporosity can be tuned really nice. And then here in this article, what we did is that we combined them with our 2 nanometer particles, and which was connected to this HPP, and then we just test them in a Suzuki Miyaura reaction in the liquid phase. And then what was really interesting that this catalyst was really stable, but not just the iodobenzene reaction, but also the chloro and bromobenzene reaction was really active and then really stable. And then here this table shows that our work was one of the best, when we checked a lot of literature data, and we find that in chlorobenzene transformation, our catalyst was really good. So anyway, so idea was that, okay, let's try this catalyst in the high pressure CO2 hydrogenation, and then this is the results. Unfortunately, the CO2 conversion wasn't too high so far here, and then there was a decreasing in it. So we still have to work on the stability of this catalyst. But on the other side, it's really interesting. You can see that there is no CO, but mostly a lot of DME was formed. More than 70 or 80% of the catalyst produced DME, which is really interesting. We tried two different HPP with similar results, with some differences in methanol and DME production, but we're still working on this. And then now we try to stabilize this HPP and then tune the porosity of such to produce, nice and high selectivity fuels. The other work what we are working on or worked so far is the copper zinc alumina systems. A lot of research is going on copper zinc alumina system. This is the one of the most frequently used catalyst for methanol synthesis from CO2 hydrogenation. And what we tried is, so usually the ratio is 1 to 3 to 6 copper, zinc, alumina in this catalyst. And usually they produce it with a wet impregnation method. So they take copper, zinc precursor, put it together with the alumina, and then they just co-precipitate them. And that's how they produce it. And what we did is that we have a planetary ball mill where the energy is really high in this ball mill. So you can reach also chemical reactions inside. That's why we call it a mechanochemical system. And then, so we put the precursor in there, and then in the dry ball milling method, we produce the same catalyst. And with XR and everything, we can see, the nice reflection of the oxides. And what we found is that, so the blue one in CO2 conversion is the basic catalyst. So with the wet impregnation. So that has a better catalytic activity. However, let's see the selectivity. So this is the basic catalyst with the wet impregnation. You can see that 60% was CO and then 40% was methanol for this reaction selectivity. However, if we used our ball mill structure, this is two different kind of ball milling, but you can see that it was the opposite. So from 60 methanol, from 60 CO, we went to 40 CO, and the methanol selectivity was way higher compared to the wet impregnation method. So this is kind of an interesting part of research what we are conducting. And then we also start working so from the literature, this sodium iron oxide and ZSM5 tandem catalyst was a really famous one, but this is the Fischer-Tropsch route. And but we tried this reaction, and where we could find really nice CO2 conversion in the Phoenix reactor with a really nice C5 plus selectivity beside the methanol and propane and other hydrocarbon selectivities. So in the future, we are still designing our new catalyst and then improving our catalyst. But beside that, these nice working catalysts, we wanna start doing the upscaling of this reaction towards industrial applications. And then what is good is that, so now we're going with this 100 milligram of catalyst with the 30 to 50 mil rate, but we can easily go up with the Phoenix. The reactor can be big enough to have and handle 1 to 2 gram of catalyst, but also we can put almost 10 or 20 or 50 gram of catalyst also inside. So in a scale-up procedure, we started to increase the flow rate and then the amount of catalyst. And then also the plan is to integrate the h-genie into this system, as the genie can produce high pressure hydrogen up to 1 to 5 liter per minute hydrogen. And then with that source and our pressure model with the CO2, we can go up into a big lab or pilot test and towards industrial applications. So thank you very much for being with me, and then thank you for having me and the opportunity that I could share these results with you. And thank you very much for your attention. And then please don't hesitate to reach me. You can find me at the University of Szeged, and you can find my contacts all the time. And then unfortunately, now I have to go due to a family tragedy. I cannot be with you more. But if you have any questions, Alishan Malik, a really good research fellow of me and an expert of CO2 hydrogenation will be with you, and then happy to answer to your questions. So thank you very much again, and then have a nice day.
Hello, everyone. I'm happy to take your questions now. This new system of h-genie, actually, this will give high pressure hydrogen like to 1.5 liter per is the maximum, like 1.5 liter, not 100 ml. I explain again. I got a question here about the h-genie for the high pressure hydrogen generator. Uh, I assume the flow rate we could get around 1.5 liter per minute, high pressure, and we are assuming to use this system for scale up of this CO2 hydrogenation process. Uh, Regarding the tolerance of catalyst to NO or SO2, right now we are using CO2 hydrogen mixture, which is 99% pure. The catalyst we are testing, we haven't tested the tolerance for NOx or SOx at present. But maybe when we try for the scale up of these operations, we will definitely look for NOx and SOx as well. To pressurize a reactor, there is a pressure module which is very easily connected with the reactor, and that has a three-way valve system which like maintains the pressure of the reactor. So the maximum operating pressure we could get like is 200 bar from this pressure module. So the pressure in the reaction chamber, it contains a system valve, a pressure sensor, and a three-way valve to set the outlet. And right now, what we are using for our reaction is between 20 to 60 bar pressure, but the system is capable of reaching up to 200 bar reaction pressure. The pressure module actually comes with the reactor. We buy it from the Phoenix, from ThalesNano. I mean, it comes with the reactor in a complete package if you need for high pressure applications. Yes, as I just told you, like the pressure module, it comes from the same company, ThalesNano. They provide the pressure module for high pressure applications for this Phoenix reactor. Absolutely, yes. This is the pressure module which comes from ThalesNano. Actually, the complete system which is installed in our lab, I explain it like this. It comes as a reactor setup. It has a pressure module. It has a flow module for the input of high pressure gas flows. Like you can introduce almost 14 different gases. You can store a mixer and you can introduce different gases at a time. And the pressure module is designed specifically to maintain the pressure in the chamber. Yeah, that's interesting. Ideally, the system was designed for liquid phase reaction, but what we found here, especially in our application, that this system is equally capable for using for gas phase reactions. And the same pressure module we are using for gas phase reactions, then it's perfectly maintains the pressure with the gas phase reactions. So we do not introduce any liquid into the system. It's purely gas phase reaction, and the pressure we maintain around between 20 to 80 bar right now, and the pressure module works perfectly fine. Uh, I do not have the exact picture right now with me for the connections, but what we are using, we are using gas lines like it's a stainless steel gas lines with a high pressure control valve. So the pressure, the flow which is coming from the gas module, it's already at high pressure and it's coming through the high pressure gas valve, and then it goes into the reactor through the stainless steel tube connections. And most importantly, the whole operation of this high pressure system is very safe and it is very easy to use. I mean, the whole system is capable of achieving to working fine at high pressure applications. The system is quite compact and it's very easy to install. I have worked with other high pressure systems like PID reactors early on, and I remember like those reactors are very heavy and very difficult to move from one place to another place. But these systems, the Phoenix systems, are very compact, very easy to use, and easily you can install them easily. They don't require much of your space, and it could be easily installed. I mean, very easy to use, user friendly. Of course, you have to maintain the gas pressure cylinder. Ideally, what we do here, we maintain a higher pressure at the gas cylinder. The pressure should be at least 5 or 10 bar more than what required in the reaction. Also, in the gas module, you have to maintain at least 5 bar pressure uh, ahead of what you need in the reaction in the reactor. So in case if you need 50 bar pressure, say in case in the reactor, you have to maintain the pressure of around 55 bar at the gas module, and same goes to the gas cylinder. Right. No, the CO2 is in the gas phase which enters the reactor. CO2 is the CO2 mixture, basically CO2 and hydrogen. We are using mostly 1 to 2 or 1 to 3 or 1 to 4 ratio of CO2 and hydrogen, and it's in the gas phase, absolutely. Actually, we have different gas modules for different gas inlets, but right now, which we are using, as I told you, we are using a mixture cylinder for CO2 and hydrogen. We are not using CO2 and hydrogen separately in separate tanks. So this is just one cylinder we are using CO2 hydrogen mixture with a different ratio. Of course, we have different cylinders with 1 to 2, 1 to 3, or 1 to 4 ratio of CO2 hydrogen. But we can use multiple cylinders with multiple entries with different gas modules. And as for the scale-up process, as we Professor Andras just mentioned, that we are going to use the hydrogen separator, high pressure hydrogen separator, that will be used for the introduction of hydrogen, and for CO2, we'll use a separate CO2 cylinder for high pressure CO2 induction. But right now, what we are using is a hydrogen CO2 mixture cylinder. And for that, only one gas module is required. Because for the pre-treatment of the catalyst, we are using a different low pressure flow system, like for the reduction of the pressure inside the reactor. This is, the pressure. The pressure module comes with the automatic control of the pressure. It displays the pressure exactly inside the reactor on the screen. There is a touch screen which you can use. Even for maintaining the pressure, there are two systems. One is manual and one is automatic. So ideally, you can use both systems. Automatic system requires a certain amount of time to establish the pressure in the reactor. So what we are doing here right now, what we do it manually, that we reach to a certain reaction pressure and then we switch to the automatic mode, and this way we save our time as well. But anyhow, you can use both modes, manual or the automatic one. And it doesn't take longer to establish whatever pressure requires in the system. And it displays exact amount of pressure in the reactor on the screen. Any more questions from the audience? I mean, you can also write to us, you can write directly to Professor Andras if you need any information regarding the system we are working on and regarding the operation of this reactor and the whole system. So we are happy to answer your questions anytime. All right, I think there are no more questions. Thank you everyone for participating in the webinar. It's really nice talking to you all. And as I said, if you have any more questions, you can write directly to us and we are happy to answer your questions. Thank you. Thank you so much. Have a good day.